simplifying the trig expressions. Tomorrow, we're going to continue working on these problems, except the only difference is that you're going to know what the answer is, which is kind of how we finished the last example yesterday. So you'll know what to work toward and where it's supposed to simplify to, so that maybe it's supposed to equal the cosecant, or maybe it's supposed to just equal the secant, but you'll at least know what the goal is. So essentially it's the same type of problems, but there's an equal sign because we're trying to get it to be equal to whatever's on the other side of the equal sign. So we're going to look at those tomorrow and on Friday, and then we'll wrap that up next Monday. So in your homework, just as I said, looking at a few problems, I thought we'd start with 62, and then we'll look at 70 and 81. I will say that with these problems, the answer or the direction that you choose might not come to you the first time. So these are problems that sometimes you have to be a little patient. You might have to start over. Sometimes it helps just to go to a new slide in Notability, or if you're using paper, just start fresh, skip the problem, try it over again. There is not just one correct way to simplify these. So that's the nice thing about it. There are a couple of different ways that you can approach it. It just depends on what you see in the problem. So saying that, if you look at number 62, we have these two fractions. And again, your goal is to simplify. Now, these fractions are being added. So you've got to make sure that you are applying correct algebraic properties to add fractions together. So it's not multiplication, it's addition. And again, it really just depends on what you think of first to approach the problem. So in number 62, Darby, what did you notice about 62 and how did you start the problem?
I noticed that 1 plus sine x on the bottom, so I used the conjugate. So I did 1 minus sine x and multiplied the top and bottom.
Yeah, so just she's looking at the left fraction, and there's a 1 plus sine x, so we can multiply it by its conjugate. And then Darby, what did you get in the numerator and denominator of that first fraction?
In the numerator, I got cosine x minus sine x cosine x, like they're multiplied by each other. And then on the bottom, I got 1 minus sine squared x.
Perfect. So distributing cosine through the numerator and then foiling the denominator. Remember, really, it's the first term and the last term. The middle terms end up canceling. So she said that became 1 minus sine squared x. So thumbs up if you did it this way. Anybody else do it this way? Give me a thumbs up. Good. Okay. We'll talk about another approach in a minute, but let's just continue working on this. So Darby, I'm going to stick with you one more time here. What did you do next after you used the conjugate process?
So I changed 1 minus sine squared x to cosine squared x.
Yeah.
Because that is one of the identities.
Excellent. So
and
using
then,
that Pythagorean identity, you said you changed it. Okay.
Yeah.
And then you continue, you're good.
And then I multiplied the right fraction by cosine on the bottom and the top so I could get a common denominator.
Good, nice. So noticing that 1 minus sine squared changed to cosine squared, the right fraction has a cosine, so we might as well multiply it by another cosine so that its denominator becomes cosine squared. Remember, you want to get a common denominator. So that then gives us cosine and then plus sine times cosine. Nice job, Darby. So now we have these two fractions. We have a common denominator. The whole goal of a common denominator is so that you can add the numerator. But remember, the denominator stays there. So when you have a common denominator, you add the top together, but the bottom of the fraction is still there. So if I had like 3/5 plus 2/5, or 3/5 plus 8/5, the denominator stays as 5. You add the numerators together. So when we add these numerators together, our sine, cosine, one of them is positive, one of them is negative, so they cancel. And then we still have a cosine plus a cosine. Well, if x plus x makes 2x, cosine plus cosine makes 2 cosine. You're adding them together. It's a plus sign. So one cosine plus another cosine makes 2 of them. So now we have 2 cosine over cosine squared. And using properties of exponents, the cosine in the numerator cancels with one of the cosines in the denominator. And then this becomes 2 times the secant of x. So 2 over cosine is really saying I have 2 times 1 over the cosine. And 1 over cosine is the secant. Questions? So I think some of you use this approach. Nice job, Darby, using the conjugate. Was there another method that you used to solve this problem or to simplify this problem? So some of you didn't say you did it this way. So what other method could you have used? Peter, what did you do for number 62?
I did that.
You did that way?
Yeah.
Did anybody find just common denominators to start with? Oh. So you could have said, I just want to find a common denominator and multiply the left by cosine and multiply the right by 1 plus sine. That would have worked as well. And then you would have had a common denominator. I could have multiplied this side by cosine, and I could have multiplied this one by 1 plus sine. And that would have worked as well. It would have given you the same exact end result. You're just starting it a little differently. So you could have just started by saying, hey, I'm just going to multiply each denominator by the other denominator to get a common denominator from the first step, instead of waiting to get that common denominator. Questions? All right, so let's go down and look at number 70. Number 70, we have a tangent squared on the top, and we have a cosecant plus 1 on the bottom. So Jack, how could we simplify number 70? What would you try and do first here? So what could we do with that denominator?
Multiply it by cosecant x minus 1.
Yeah, let's use that conjugate fact. Multiply it by cosecant x minus 1. We use the conjugate fact a lot. So what does the denominator become, Jack, if you multiply cosecant plus 1 times cosecant minus 1?
Cosecant squared minus 1.
Yeah. So what do you think you should do on the top? So on the top, you can distribute that through. So, and I think maybe a lot of you chose to do this. So I'm going to distribute it through just for you to see what it looks like. I believe a lot of you did the distributing process here. And if you distribute it through, you're just distributing tangent through. So we have tangent squared times cosecant minus tangent squared. So Jack said to use the conjugate. And again, the whole goal of using the conjugate is so that you can then replace that part where you use the conjugate. So in this case, we have cosecant squared minus 1. And that cosecant squared minus 1 is really the tangent squared. So now our denominator becomes Not the tangent squared. I'm sorry, the cotangent squared. I got my wrong trig function in that identity. There we go. Get that correct. So our denominator is the cotangent squared. And then in the top, we have the tangent squared cosecant minus the tangent squared. So if you look at the denominator, what can you change the cotangent squared to? Noticing the functions on the top. So what identity could we use to change the cotangent squared? How else could you write it? Peter, what other way could I write cotangent squared?
Tangent squared over 1.
Yeah, so 1 over tangent squared. So the bottom, I could change cotangent squared to 1 over tangent squared. Now, if you look at the top, we distributed the tangent through the parentheses initially. So we distributed tangent through once we multiplied by the conjugate. I'm going to say, let's take that tangent back out, because I can see in the denominator that there's a tangent squared in the denominator. So instead of having it distributed through, let's keep the tangent squared separate from the numerator as well. So if I pull it back out, we end up with the cosecant minus 1, because that's the conjugate we initially multiplied by. Peter, when you divide by a fraction, what are you really doing when you divide by a fraction?
Multiplying by the reciprocal.
Yeah, you're really multiplying by the reciprocal. So this denominator here, where we're dividing by 1 over the tangent squared, that is really saying I'm multiplying by the tangent squared over 1. So dividing by a fraction is really multiplying by the reciprocal. And now in the numerator, we have a tangent squared and a tangent squared. How many tangents do you have then, Peter?
You would have 4.
You have 4. Just like x squared times x squared is x to the 4th, tangent squared times tangent squared is tangent to the 4th. So sometimes the numerator, we end up not distributing through, because it's going to end up combining with something from the denominator. And in this case, initially distributing tangent squared through that numerator, the conjugate, it ended up not being the way to work through the problem. So kind of just thinking like, what do you have in your fraction? Is there something in your denominator that might be able to combine together with the numerator? And that would be that tangent squared. So instead of distributing it through, we're going to just keep it outside in that factored form so that we can combine those two tangent quantities together. Any questions on 70? So just quickly looking at 81, it wasn't supposed to be confusing, but I think sometimes the questions or directions in the book are a little different. This one wanted you to use trig substitution. I think it used the word trigonometric substitution. So they give you an algebraic equation, and this is a little like glimpse into calculus, hence pre-calculus. They're telling us that we have the equation, the expression, the square root of x squared minus 9. And then over here, it says x is equal to 3 secant squared. Well, trig substitution works exactly like algebraic substitution. If you have an x squared and they're telling you what x is, you replace x with that quantity. So we have 3 secant theta. X is squared, so this 3 secant is squared. And then we have minus 9. So Jenny, when you square 3 times secant, what does that become when you square that?
9 secant squared.
Yeah, you get 9 secant squared. And then it's still minus 9. So Jenny, if we're working underneath the quantity here, What do you notice about 9 secant squared minus 9?
They have a common factor of 9, so I took that out.
Excellent. And then you were left with secant squared minus 1. What'd you do next then, Jenny?
I replaced secant squared minus 1 with tangent squared.
Yeah, so 1 plus tangent squared equals secant squared. So that means secant squared minus 1 is going to be equal to the tangent squared. So now we have 9 times the tangent squared. And that is equal to what, Jenny?
3 times the tangent of theta.
Yeah, 3 times the tangent of theta. So taking the square root, they're both perfect squares. They're both being multiplied together. So the square root of 9 is 3. The square root of tangent squared is just tangent. Nice job, Jenny. So those are the questions that I saw on the homework form. If you want to go to Google Classroom, in Google Classroom is the practice worksheet for today. So travel over to Google Classroom and find the section 5.1 practice worksheet. Peter, question?
I was gonna ask you, we could go over 45.
Yeah, of course. Let me go back. 45, you said?
Yeah.
Yeah, let me find it. Here it is. Yeah, let me just cut it. Here. All right, so looking at 45, we have cotangent squared minus cotangent squared times cosine squared. What'd you do first, Peter?
I made the second cotangent squared cosine squared over sine squared.
Okay, that'll work, but before you do that, I believe the directions wanted you to factor. So if you factored first, Peter, how could you factor this? What do you notice?
Would you take out a cotangent squared?
Yeah, so take that out first, and then you have 1 minus cosine squared. Then you would do exactly what you said. So then I would change the cotangent squared to be cosine squared over sine squared. And you can change this quantity in the parentheses that's remaining to sine squared. So sometimes doing an algebraic step first, instead of trying to do a trig step first, then kind of switches the problem a little bit and it pulls out that cotangent. So yes, you need to change cotangent, but I would say factor first and then change the cotangent.
Miss Kane, I have a question about
Yeah.
that. So I changed the second cotangent, the one that's attached with the cosine,
Mm-hmm.
to cosine squared over sine squared, and then I made it 1 over sine squared. So then it was, and then I changed the first cotangent, so it was cosine squared over sine squared minus 1 over sine squared. And then since they have the same denominator, I just subtracted that to get cosine squared minus 1 over sine squared. And then I had cosine squared equal to negative sine squared. And then my final answer was -1.
I'll have to look. If you can stay on, Peter, and maybe share your screen so I can look at it. I think I think you were missing this extra cosine in the back. There's still this extra cosine because it's cotangent
no.
sine.
Oh wait, I see what I did wrong there.
Okay, all right.
Never mind.
But I can look at yours later too, Peter. Anybody else have questions? I apologize.
I accidentally, when I multiplied the cosine squared over sine squared by the cosine squared.
Yeah, did you multiply those? I think Peter's frozen. Okay. So if you look at the practice worksheet,